My name is Russ Kohler. I'm the president of the Association of Energy Engineers here in Hawaii chapter. The Association of Energy Engineers is the only international energy association worldwide. With I think we're up to about 150 chapters worldwide. Anyway, we here in Hawaii are very interested in anything new with geothermal, and we're looking forward to this presentation. I'm going to turn it over to Peter Sternlight. He can introduce Sustainability Energy Hawaii. All yours.
Thanks, Russ. I'm with Sustainable Energy Hawaii. We're co-hosting this webinar with the Association of Energy Engineers Hawaii chapter. And Sustainable Energy Hawaii is a clean energy advocacy and research organization based on the Big Island in Hawaii. And we've been operating now for going on 6 years, and we're very active in policy recommendations, formulations, and we just are in the process of publishing a very extensive scientific report in collaboration with the Geological Survey of Finland, where we've taken the entire Hawaiian economy and modeled it as if it were run completely on renewable, carbon-free energy. And we expect that to be hitting the streets probably within the next 3 to 4 weeks. So we're very excited about that. So I think I'm going to hand it back to Russ, and we can get going.
Thank you, Peter. It's a very exciting time for geothermal in the world, but frankly, the United States for sure. And you're going to hear some very exciting news from Matt today on all the great stuff that Quaise Energy has been doing. And one of my questions you can answer at the end is, will you guys be willing to take a look at projects in Hawaii? But for now, I want to introduce you to Matt Houde, Quaise Energy. All yours.
All right. And thank you for inviting us to this webinar and for everyone in attendance. This is definitely, as Russ said, some very exciting times in geothermal. Today, I'm going to talk about Quaise Energy and sort of our outlook and approach into how we want to develop and scale geothermal. And if there's one word or phrase I could leave with you in relation to Quaise and sort of our vision, it's going to be this sort of second line here in the lower left, which is produce terawatts, or geothermal at the terawatt scale. If you may be familiar, world energy demand, not necessarily energy consumption, but online power demand is on the scale of terawatts, something on the order of 15 to 20 terawatts. That's a number that includes all use of electricity, all use of burning fuels for transportation, for heating. And when we talk about decarbonizing the energy system of the US and the world at large, this is the scale that we need to think of. And Quaise's vision in terms of how we approach geothermal is to realize exactly that, is develop an approach to geothermal that can produce geothermal energy at the terawatt scale, at the same scale at which the existing oil and gas industry adds energy products to the world energy system every year. Just a brief note in some of our current investors, partners, and industry relationships. A few I'll highlight here is that to date, Quaise has raised close to 95 to 100 million in private venture capital, and we are planning to raise a larger sum sometime this year on the order of 200 to 300 million to realize our goals. Certainly benefited from our investors, our academic and government partners, especially those within the Department of Energy that helped us very early on with an ARPA-E funded project we had on our drilling technology, and certainly wish to continue those relationships in the future. So where I'd like to start is framing the energy system and decarbonization in general, and why it is a serious challenge to address our decarbonization goals without geothermal. This chart has been put together utilizing various agencies that put together annual energy outlooks. I do believe it is not only a few years outdated, but I'll note these projections do tend to be outpaced by technological innovation and energy deployment. But I do think, as a rough order estimate, these are accurate in showing that with our current projections of how we are approaching decarbonization in the energy system, we aren't necessarily close to this goal of realizing a fully decarbonized energy system worldwide in 2050. Now, that is owing to several factors, one being, of course, that energy transitions tend to have taken place much slower than they are currently, although they've not necessarily had the demand or constraint that we currently have with country and nationwide goals to decarbonize their energy system. But something that I think is missing in these projections that would affect the picture is the availability of a scalable, power-dense source of firm, or what you could call baseload clean energy. As it stands today, the beyond wind and solar, the two sort of leading clean energy deployments today, which are intermittent, our main available baseload sources of clean energy to date have been nuclear fission, which is quite limited in its ability to scale rapidly and worldwide owing to various economic and geopolitical constraints. But sort of an untouched fruit here in having a source of clean, firm power for the energy system of the future is geothermal energy. Geothermal has been developed and deployed worldwide over 100 years for electricity generation. If you'd like to expand that to use cases of heating, you could say geothermal is one of the oldest sources of energy we've had to date in the form of hot springs that would be used for various heating needs. But for the past 100 years, geothermal has been tapped into as a source of energy to produce electric power at temperatures ranging typically from 200 to 300 degrees Celsius. More recent progress and deployment of geothermal has actually focused on lower temperatures that have been accessible with some of the technologies available today. But for Quaise, where we're quite interested in scaling geothermal more rapidly, is targeting super hot temperatures. So kind of improvising here on some missing slides, where Quaise is interested in developing and advancing geothermal to that terawatt scale is targeting something we call SuperHot EGS. And let me provide some color and different formats of geothermal and how SuperHot EGS differs from those. So to date, the vast majority of geothermal deployment involves tapping into naturally occurring geothermal reservoirs, which we tend to refer to as hydrothermal reservoirs, where various geologic conditions give fruit to cold water circulating down various faults and fractures to a point where that water heats up at depth and is then conveyed up through other faults and fractures that can then be drilled into with various wells to produce that hot water or hot steam at the surface for electric power generation. Where that naturally occurring geothermal systems occur today has been a great boon to those countries and regions that can tap into those naturally occurring resources, but it's very limited in scale. You typically don't find these reservoirs beyond locations in countries that are nearby existing plate boundaries, where you have the confluence of a few subsurface properties and trends, such as very high heat shallow to the surface, as well as the geologic conditions and water availability necessary for that water to flow down the surface and up through the subsurface to heat up to a temperature that is economic for producing electricity. And so for the past 30, 40 years, there has been a great deal interest in enhanced geothermal systems, whereby we drill not into naturally occurring hydrothermal reservoirs, but we simply drill into hot rock. We then execute various hydraulic fracturing techniques, similar but not identical to what's done in oil and gas today, for creating a fracture network that can then connect two or multiple wells, so that now you are, in essence, creating or engineering the heat exchanger between the rock. And we utilize that fracture network and connected wells to pump cold water down one well and produces hot water and steam through a production well. So this approach very much removes the constraint of finding these naturally occurring reservoirs that are quite limited in scale and region. But for EGS, it is a challenge to make these systems economic at lower temperatures. And I think where the progress that EGS has been to date, as well as where EGS projects today are going to be developed and in the foreseeable future, it's still going to be in regions that have a very high heat gradient, such that we can drill to relatively shallow depths for creating that EGS reservoir and producing the energy from the subsurface. For Quaise, we would like to marry EGS with drilling deep to much higher temperatures and accessing what we are calling SuperHot rock or SuperHot temperatures. And we use this word to basically describe temperatures in the subsurface that exceed the critical point of water. This is, in terms of temperature, something on the order of 375 degrees Celsius. And the reason for accessing these super hot temperatures is this chart on the right here, which is being able to produce energy from a geothermal well, much comparable to the types of energy that are produced from oil and gas today. When we get to these super hot temperatures, we have much higher energy, you could say energy density within the fluid. In other words, the enthalpy of this fluid is much higher than the types of geothermal systems produced today. As well, when we're producing that hot fluid or steam at the surface, there's a greatly improved conversion efficiency in terms of turning that thermohydraulic energy into electrical energy via a steam turbine generator, which is the common mechanism for converting sort of hot steam or water into electricity today. And where this can yield benefits is namely being able to achieve much more competitive levelized cost of electricity, scalability in terms of the power density we can produce from these wells. Again, super hot geothermal wells could potentially be producing energy on a similar scale to what oil and gas wells produce today. So when we are interested in getting the oil and gas industry and workforce compelled to develop geothermal resources and geothermal energy, I think it's an enticing point to show an approach to geothermal that produces energy at similar cost to what oil and gas does today by going super hot. The challenge, of course, for this approach is how do you drill deep enough, which is what I will get into in a later slide, as well as with our drilling technology we are developing at Quaise today. This chart is just showing a sort of current status on geothermal production today in terms of temperature and depth. Again, the vast majority of these wells are occurring, like I mentioned earlier, in that 200 to 300 degrees Celsius range, typically shallower than 3 kilometers depth, which is also fairly analogous to where oil and gas resources are developed today. One thing I want to point out is there have been at these naturally occurring geothermal systems a number of wells that have been drilled into these super hot conditions with respect to temperature, as well as with respect to the depth that we would like to target. And I'm not sure if you can see my mouse here, but in essence, the region we would like to target for developing super hot EGS at scale in the US and worldwide is targeting this blue region in the lower right and actually going much deeper than what is shown on this chart, so that we are able to develop competitive geothermal energy in locations that aren't even thinking about geothermal electric power generation today, where lower geothermal gradients are observed. And that is actually what's being shown by the bullets I just pulled up here with the animation. The yellow bullet I would like to highlight is the Cape Station project that's being developed by Fervo Energy. I'd say Fervo Energy has been the pioneers in the EGS space the past 5 years in developing the most successful EGS demonstration to date, and they are currently developing the first large-scale commercial EGS project in Utah, targeting this 200 Celsius temperature region at a depth just above 3 kilometers. Where we would like to take that approach to EGS is to the red bullets you see here in the lower right, first targeting 400C at a relatively shallow location, likely a location where you have some sort of volcanic or magmatic anomaly, before then beginning to progress the depth at which we can develop this super hot EGS resource. This chart kind of reemphasizing the point I made before with the appeal of doing super hot EGS. It really at the end relates to how much power, electric power, we can potentially generate at the wellhead. You'll see with the stars here, with our initial pilot demonstration, we would like to demonstrate output on the order of 15 megawatts of electric power per well. With learnings from that initial demonstration and subsequent demonstrations, we would like to see geothermal projects developed at a scale such that we're producing on the order of 35 megawatts of electric power per well. And I think this is a pretty compelling number if we can achieve it, because if you look at oil and gas wells producing on the order of 1,000 barrels per day, which I think is a fairly average oil and gas well in today's industry, that's producing the equivalent of 25 megawatts electric power. And so if we hit these numbers, we're producing geothermal wells that in terms of energy density look more like oil and gas wells than the geothermal wells that have been developed over the past 100 years. How does that relate to cost? I think with a lot of geothermal development so far, and especially the EGS fields that are going to be developed in the near term here, we're looking something on the order of $80 to $150 per megawatt hour for the levelized cost of electricity. We believe as long as we can maintain linear increases in drilling costs and the stimulation costs to create these fractured reservoirs, we can achieve something much more on the order of $45 to $60 per megawatt hour, which makes geothermal competitive, if not superior in cost, to the coal plants and combined cycle natural gas plants that are on the grid today, providing baseload power in our current energy system. So at Quaise, what we're seeking to achieve is unlocking a pathway to this cost-competitive, scalable geothermal through SuperHot Rock. We believe these SuperHot Rock resources are widely available in the Western U.S. at depths of 7 to 12, 15 kilometers. And if we can achieve drilling and creating reservoirs at 12 to 15 kilometers, we've unlocked large swaths of the eastern U.S., and this also applies to much of the world at large. We can scale geothermal beyond the locations it is today and achieve an approach to geothermal that can deploy annually at the scale of gigawatts to tens of gigawatts in annual installations. Our technology development within the company is focused on two prongs, one of which is developing the technologies and techniques for developing these EGS reservoirs at these very high temperatures, which is not a trivial feat with respect to the understanding of the rock, as well as the equipment, tools, and electronics that are required downhole. The second prong, which I think is the most critical prong here, is our millimeter wave drilling technology, which is an approach we've been developing to drilling that we can believe enable this economic access to these super hot temperatures at great depths. Because the challenge, of course, in unlocking super hot EGS at scale today truly is drilling down to those target depths. There's only less than a handful of locations in the US where we think we can hit these super hot temperatures above 5 kilometers depth. If you're going deeper than 5 kilometers, doing this with conventional drilling technologies could become exponentially more expensive and more challenging, owing to the equipment required failing at these higher temperatures, drill bits requiring more frequent replacement, and overall much slower drilling owing to the increasing non-productive time required to basically replace these drill bits and components downhole as you are drilling into deeper and hotter rock. This slide kind of re-emphasizing the argument I've been making on the past few slides. How does our approach to geothermal differ from conventional geothermal? I think the three sort of prongs to think about here are: one, exploration risks. By utilizing these EGS techniques to create geothermal reservoirs independent of those naturally occurring geothermal reservoirs. We greatly reduce, if not eliminate, exploration risks, as not only are we not targeting these naturally occurring reservoirs, but we also are not necessarily targeting those heat anomalies. We are simply drilling to the target depth with our drilling technology and creating the reservoir at those depths and temperatures. The drilling technology is intended to reduce the drilling costs that are expected to become exponentially more expensive with depth and temperature, again, owing to those very high temperatures. And finally, power output. Producing geothermal wells, energy output similar to oil and gas wells compared to the geothermal wells in operation today. And so there's a lot of promise and value here, provided we can execute on the technology and development roadmaps that we are currently progressing through. What is this millimeter wave drilling technology and how does it work? Our basic approach is to replace conventional drilling, which involves mechanical drill bits, downhole tools, mud motors, drilling muds to circulate rock cuttings into and out of the hole. We are intending to replace all of those components essentially with an energy matter interaction by delivering high power microwaves down a pipe in the hole called a waveguide to rapidly heat and ablate the rock material that is at the bottom of this hole, and then remove that material with a purge gas that we are circulating down our pipe. So we are generating this energy at the surface with a device called a gyrotron. We're transmitting that energy down this pipe, which is the only component downhole, which greatly simplifies our downhole assembly compared to conventional drilling. Sending that energy down this pipe with a purge gas that we are injecting at the surface. This purge gas will mostly be nitrogen, but in some deeper settings, we may switch to argon at a certain target depth. And we utilize this energy and purge gas to both destroy the rock as well as remove the material we're producing from our drilling process out of this hole to convey it to the surface. So the drilling process does look fairly analogous to air drilling, done widely today, mostly in mining, but has also been done for oil and gas drilling, has been done in some geothermal drilling campaigns where air drilling was advantageous. For us, because we are producing rock particulate from this drilling process that is much smaller than traditional cuttings, we have confidence that an injected purge gas fits the bill in terms of removing the material out of the hole while we continue drilling. Some of the key features here of our millimeter wave drilling process. The first is how we are generating this microwave energy at the surface, which is this device shown here called a gyrotron. Gyrotrons have been around for about 60 to 70 years and have primarily been developed for nuclear fusion research. And in nuclear fusion, the reason they use gyrotrons is that they want to transmit very high power microwaves into a reactor, what they call a tokamak, and use that microwave energy to heat a plasma that they've ignited to temperatures where a nuclear fusion reaction takes place. The millimeter wave drilling technology was conceived about 15 to 20 years ago by a researcher at the MIT Plasma Science Fusion Center by the name of Paul Waskoff, who had an epiphany when learning about geothermal drilling to say, well, if we use these gyrotron devices for heating plasmas to millions of degrees Celsius, why don't we try using them for heating rock to 2,000 to 3,000 degrees Celsius for the purposes of ablating and drilling through rock? And that's where Paul got the idea to start to develop the fundamentals of millimeter wave drilling. I'll be honest, you are talking to a geological engineer here, not a microwave engineer or fusion researcher. And so I may not be able to fully explain in clarity the full details on how a gyrotron device will work. But to point out some of the key components, gyrotron is essentially a large vacuum tube to which you are feeding a high voltage input of electrical energy. Within that vacuum tube, that electrical energy is becoming an electron beam transmitting between a cathode at the bottom of the tube and an anode at the top. And within that vacuum, or outside of that vacuum tube, is a very powerful magnet, most often a superconducting magnet that is applying a very strong magnetic field within the cavity of this vacuum tube. And when the electrons within that electron beam see this magnetic field, they begin to gyrate in a helical motion. They begin to collide with each other. And that collision and kinetic energy is eventually converted into microwave energy, which then can be directed outside of this vacuum tube and into a waveguide transmission line from which it can be conveyed from the gyrotron source to the intended target, which in our case is the borehole. I think a key aspect of this drilling, millimeter wave drilling assembly and approach is how we are transmitting these millimeter waves from the surface to the downhole environment. And that is accomplished with metallic corrugated waveguide. Waveguides were initially conceived, again, similar to gyrotrons many decades ago, initially with the purposes of long distance communications. And they were quite thoroughly explored for their ability to convey energy, or in this case, information, tens of kilometers long distances for the purposes of long distance communications before the advent of fiber optic waveguides came about, which were able to accomplish this goal much more successfully with smaller components. But fiber optics are, in essence, strands of glass waveguides that convey light energy over long distances for the purpose of transmitting communications. For us, we are interested in transmitting much larger amounts of energy through larger sized pipe for the purposes of geothermal drilling, which is why we look at waveguides and this millimeter wave spectrum for how we convey this microwave energy from the surface to the downhole environment. And the waveguides and frequencies that have been explored for nuclear fusion research are well suited for our goal of millimeter wave drilling. And the types of sized pipes, say 4 to 4.5 inches, that we expect to use for geothermal drilling in these sort of theoretical ideal simulations, we see that we can transmit this energy several kilometers, 10 to 20 kilometers, while losing only about 5 to 10% of that energy in full. Now, in practice, we certainly expect our transmission efficiencies to be below that, but for early iterations, we're confident that for drilling distances of 10 to 12 kilometers, we'll be able to maintain energy transmission efficiencies higher than 50% as long as we execute successfully on the engineering and assembly of this downhole waveguide for conveying that energy downhole. A few notes on the drilling process itself. I've kind of moved past how exactly microwaves are drilling through and destroying this rock. And the process is actually a process that we, I think, on this audience are all familiar with, which is dielectric heating. This is basically the same process that is used in your microwave oven when you are using microwaves to heat up your food. Food, and especially the water within that food, is a dipolar dielectric material. When you convey microwave or RF energy through a dielectric material that has various molecules that have this dipolar moment, they see that energy and they begin to want to oscillate, move around, vibrate. This is what causes a temperature increase in the food. With our drilling process, we are doing exactly that, but we are transmitting such high amounts of energy into the rock to be absorbed that not only does that rock heat up, but it begins to change phase, it begins to melt, and it eventually begins to vaporize. And it is this combination of melting and vaporization by which we are able to ablate this solid rock into a very fine particulate matter that we can then convey out of our borehole environment through this purge gas that we've injected at the surface. One interesting feature I'd like to note here in relevance to Hawaii is we observed early on that one of the ash byproducts we see from our drilling process are very fine strands of rock melt that are fairly analogous to Pele's Air, which is a very commonly observed volcanic deposit in the volcanoes of Hawaii, where we see melt droplets that are suspended in the air, and while still in their liquid phase, are stretched out to form these long fibers. So the ash or rock cuttings we're producing from this drilling process are very analogous to the types of volcanic products we see in a volcanic eruption in Hawaii, which I think is kind of interesting as a geologist, geological engineer myself. Over the past couple years, we've done various experimental campaigns of the millimeter wave drilling process to validate some of the fundamentals as well as the approach to drilling in the lab while we develop and build the first field deployable millimeter wave drilling systems to mobilize for the first field trials. What I'd like to show on these two slides here are some progress in lab experiments we performed 3 years ago at our Houston Engineering Center. This was a fairly small hole that we drilled with a relatively low amount of power. We were using about 5 kilowatts of output microwave power, and we were also using a device called a klystron, which is a close cousin of the gyrotron, but not the device that we'll be using for future and current testing. What you see here in this photo is a rock target in the lab and a borehole, which is shining quite brightly. That pipe you see going into the borehole is a waveguide, which is where the microwaves are being sent down. And the rock cuttings are basically being produced out of this borehole annulus and blown out by the purge gas that we are injecting. And that's what you'll see here on the video I'm showing here. You'll see what look like sparks to be coming off of the hole, and that is actually this hot rock melt that is, of course, pretty high temperature once it is bladed off the rock surface. Here in this later video, you're seeing that hole begin to deepen. We monitor the drilling progress with various remote diagnostics, probably most importantly, a radar diagnostic that tells us the depth to which we've drilled. And as we continue to drill and monitor that progress, we can, in this lab experiment, stroke the rock into and out of the waveguide to deepen the hole further. What we are doing in the lab today is now doing away with sort of this translating rock target, and we are beginning to translate our waveguide down into the hole with a drilling rig and dynamic waveguide system that we are actually currently testing at our Houston facility today out in a yard setting. So in terms of the current progress, we are drilling with a lot more power than the videos you just saw, drilling with on the order of 50 to 100 kilowatts of output microwave power and drilling at speeds exceeding a meter per hour for borehole diameter sizes ranging 3 to 4 inches in diameter. In this month and over the next month, we are validating that drilling recipe with a drilling rig, drilling shallow rock targets in place outside our facility, ranging up to 10 feet depth. And that is being done in preparation for our first field trial of the drilling technology that is going to be mobilizing sometime in April or May of this year. I think I've gone over some of these points, but just to reiterate some of the benefits of millimeter wave drilling, a strong one is the simplification of the downhole assembly that we believe will negate the limitations to drilling to higher temperatures at greater depths. Today, we are able to drill into very high temperature settings with conventional drilling, but not only is it slow, it is limited, I think, in the depth at which we can go, owing to the fact that as we go deeper, we aren't necessarily able to continuously circulate the drilling muds and drilling fluids that can maintain cool operating temperatures for all of the equipment involved in a conventional drilling assembly. By comparison, millimeter wave drilling involves one downhole component, which is this pipe, the metallic waveguide. And so we remove the types of tools and electronics that would be inclined to fail at these higher temperatures. Another important point is the drilling process itself is insensitive to rock temperature and rock hardness, which we believe gives us an ability to drill not only at higher rates of penetration in deep, hot, hard basement rock, but also maintaining these rates of penetration as we go deeper, which is not the results observed with conventional drilling today. We believe by scaling up the drilling process to this 1 to 2 megawatts of output level, we can reach target depths of 10 kilometers in 100 days, which I think greatly improves not only the scale and speed at which we can drill these holes, but improves the economics as well, given that in drilling time equals money. And that's really the gist of why we believe millimeter wave drilling is worth doing, is that it is a cheaper economic route to drilling these super hot wells independent of depth. One final point I'll mention on the drilling process is that we don't intend for millimeter wave drilling to be a catch-all solution for all drilling applications. The advantage of millimeter wave drilling is strongest for drilling deep, hard basement rock, and it is not advantageous for drilling at shallower depths or through sedimentary rock that is softer. And so how we envision deploying this technology in the field is a hybrid type drilling operation where we start at the surface with conventional drilling, drill until we reach hard, hot basement rock where conventional drilling begins to slow down. And only at that point do we switch to the millimeter wave drilling assembly to continue drilling to our target depth. Some of the challenges I'd like to note, of course, just to be honest, with millimeter wave drilling. One, of course, is that we are repurposing technologies that have been developed for one-off nuclear fusion research projects and repurposing them for drilling applications in the field where we're taking them out of a controlled lab setting and putting them out into robust field operation where they can be exposed to a variety of elements, whether that's high heat, whether that's cold, freezing temperatures, rain, wind. These are all conditions these technologies have not been exposed to date. And so much of the work our engineering team has been focused on over the past couple of years is building the packaging for these systems such that they can be mobilized into a field setting and be protected from those elements, as well as being robust for this type of operation we're doing with drilling, which is quite different from the types of one-off research experiments that have been used for in nuclear fusion research to date. Another challenge I'd like to note is drilling very, very deep holes. To date, there has been only one well that has been drilled to exceed more than 10 kilometers vertical depth, and that was the Kola borehole drilled by the Soviet Union. One thing I'll note about that borehole was that they took about 20 years to drill that hole to its target depth. And so there's certainly been tremendous improvements in conventionally drilling to go deeper at much higher speeds. This is a shared challenge for our drilling approach, as well as competing novel and conventional drilling approaches to access these temperatures, is how we drill the deepest boreholes to date and do this repeatedly such that we can unlock access to this super hot geothermal resource independent of locations where geothermal is favorable today. And so that implies a host of challenges for wellbore stability with our drilling technology. One is, of course, understanding how we can drill deep holes in this underbalanced type drilling condition where we're not utilizing drilling muds to stabilize the borehole while drilling. Another important one that I have not noted much on our previous slides is the vitrified liner, which is an outer region of the hole that is molten, but is not necessarily ablated or vaporized. And so this outer layer stays behind in the hole and remains as sort of a glass ceramic liner, somewhat analogous to, say, obsidian as a rock glass that remains in our borehole post-drilling. And certainly a large work stream of research we plan to do over the next couple of years is understanding how we could potentially optimize this vitrified liner, as well as the thermal alteration to the borehole, to understand whether we can use that liner to potentially stabilize this underbalanced borehole for drilling to much greater depths than what we do today. Some notes on the roadmap. I mentioned about 15, 20 years ago is when this concept came about at MIT. We founded Quaise in 2018 with the purposes of commercializing this drilling technology, and over the past couple of years have demonstrated significant improvements in the drilling results in the lab compared to what's achieved at MIT. What we are doing today is taking these technologies out of the lab and into the field, which we plan to do this year with our first field trial, targeting an initial drilling depth of 100 meters before scaling that to a kilometer depth in 2026. And by 2027, 2028, we'd like to optimistically say we mobilize millimeter wave drilling for its first drilling campaign for a geothermal project. Now, most of the discussion today, I've focused on the drilling technology, but I would like to note that there are a variety of technology challenges and needs for developing this SuperHot EGS resource at these depths and temperatures. Drilling is one side of the equation, but a very important aspect is how we complete these wells to tolerate the temperatures and loadings that they can expect. So this is the casing and cement that we would expect to install downhole for this permanent wellbore completion, ensuring that it keeps the borehole open and is able to accommodate both the reservoir creation aspect as well as the production from this EGS reservoir. And there are a host of materials involved in this reservoir creation process that we need to mature to withstand these higher temperatures at greater depths. Things like proppants that are going to be in place within the fractures to keep these fractures open while we are producing the hot fluid from the reservoir. Things like the casing itself, the metal pipe lining this wellbore, ensuring they can tolerate those high temperatures. There's a great deal of work in terms of modeling and field demonstration to understand how we best create these reservoirs. I mentioned earlier some of the EGS projects that have been executed to date at lower temperatures, and even at that lower temperature, but also applied to our super hot temperature target. There are still learnings required in understanding the best approaches to creating these fracture networks that connect multiple wells, ensuring water is flowing uniformly through those fracture networks such that it is not concentrating in one zone and risking rapid thermal drawdown, or what we call short circuiting in the EGS space. There's a great deal of learnings needed in that focus before we can successfully develop these EGS reservoirs at any temperature, let alone super hot EGS temperatures. One area of research I would say novel to super hot EGS and what we're doing at Quaise is the rock fracture mechanics in the brittle ductile transition. By targeting these temperatures, we expect rock in these regions to nominally fail more in a ductile manner, where deformation is not necessarily localized in singular planar fractures, but could result in more of these distributed complex cloud fracture networks noted here. These images and charts are based on some lab research that's been done in Japan over the past couple years, and Quaise has currently been involved with lab experiments in collaboration with EPFL University in Switzerland to better understand these fracture mechanics at the types of temperatures and pressures where rock begins to become nominally semi-brittle to even ductile. And that's something we are planning to de-risk here in the coming years with some lab experimental collaborations we are helping support with universities like EPFL and additional universities that can help us understand key aspects such as the interaction of fluids and rocks at these temperatures and pressures. One other area of research, of course, is the conceptual model for EGS and what is the best conceptual model for creating a well-connected fracture network between wells. The past 30, 40 years of EGS has focused on this shear stimulation model where you inject cold water down open hole intervals to stimulate and enhance permeability along large, naturally occurring faults and fractures. Not only has this approach had limited success, but it's also proven to be somewhat risky with respect to inducing seismicity, resulting in projects being shut down in Switzerland and South Korea. And so in the past 5 years, there's been a lot more momentum in this planar hydraulic fracture model that is much more identical to what's done in oil and gas today. And this is the model that Quaise Energy, I believe, is currently leading with in terms of how they plan to create a fracture network. In other words, drilling long lateral wells and connecting those wells with tens, if not hundreds, of hydraulic fractures that you are initiating at the wellbore that are conceived to be somewhat of this planar geometry. Some of the models that we are interested in exploring for SuperHot EGS are this hybrid fracture model, which is a combination of the planar hydraulic fracture and shear stimulation along natural fracture model. So in other words, how best can we utilize the planar hydraulic fractures and the natural fractures already present in the formation to create a well-connected EGS reservoir between multiple wells? And the final model, which is more speculative at this point, but could prove more omnipresent at these super hot temperatures, is this cloud fracture model that's been observed in lab experiments with semi-brittle ductile rock. In other words, creating a much more complex omnidirectional fracture network owing to the varying fracture mechanics at these temperatures and depths that we are planning to target. One final area of research on EGS I'd like to touch base on are the reservoir models and fracture modeling for EGS at these conditions. No projects for fracturing or even geothermal to date have really targeted the temperatures and rock deformation regimes in terms of brittle versus ductile that we are targeting. And so there is a need to mature the types of reservoir models that are able to accurately simulate how we fracture and produce heat from those fractures in a reservoir over the duration of years, the tens of years. And so this is an area of research we have supported with a researcher at the University of Iceland to best understand how the changes in temperature and pressure and rock mechanics may affect the evolution of these reservoirs over the period of production. And this is certainly an area of research Quaise will continue to support in the future as we begin to gain potentially some real field data and learnings to test these hypotheses from the geothermal projects we plan to develop in the coming years. I think with that, this is kind of hitting my last few slides here. So I'll just note in terms of achieving an nth of a kind super hot EGS project, we want to achieve this 20 megawatts electric power per production well value, being able to produce that fluid over periods of greater than 20 years at these competitive levelized costs of electricity. And very important to us, EGS in general, minimizing, if not eliminating, the risk of impacts from induced seismicity. And with that, I will wrap the presentation and open things up for Q&A. And apologies if I went a little long there.
Okay, we have quite a few questions in the Q&A chat area, and I think that some of our panelists have questions as well. First question came in from Mitch Ewan. Can you talk about horizontal drilling?
Yes, great question. So for our first field demonstrations, we are focusing on drilling simple vertical wells, but we are beginning to explore the potential for directional drilling with our millimeter wave drilling technology. What we've seen so far is from a sort of modeling theoretical point of view, it is plausible, albeit not trivial in terms of engineering the downhole waveguide to be in drilling process to turn directional. We aren't necessarily of the opinion that we need fully lateral wells for these EGS reservoirs, although that has certainly been very successful for Fervo Energy, as well as being the dominant approach in oil and gas today with directional drilling. And so right now, our leading hypothesis is we want to explore directional drilling on the order of 30 to 60 degrees inclination with millimeter wave drilling technology for the purposes of having better success of creating an EGS reservoir.
Okay, safe to say you're just not there yet. You're not sure you need to do it.
That's right. But we do believe directional drilling capability is necessary, just not necessarily the full lateral drilling that we see today in oil and gas.
Okay. I'm going to switch to the chats from scalability. What are the biggest technical challenges in scaling this drilling technology for widespread commercial deployment?
Yes, well, we certainly have to tackle the technical challenges to the drilling process. The way I like to put that simply is we need to get power down the hole, we need to get stuff out of the hole, and we need to keep the hole open. So the first question is ensuring that we engineer the downhole waveguide effectively to transmit this energy over long distances with low attenuation, or in other words, with very high efficiency so that we are not losing that energy to ohmic losses into the pipe or waveguide. We then need to be sure that we can successfully remove these rock cuttings, the ablated rock material, out of this borehole with our circulating purge gas. And finally, we need to ensure that we are stabilizing this borehole such that the borehole does not collapse onto itself as we go deeper, especially given, as I mentioned before, that we're drilling under balance. Just one final point I'll note on the scalability challenges is there's definitely a big challenge with that supply chain I mentioned, that the gyrotrons and waveguides as they've been manufactured today is for one-off fusion and research experiments. And so we are working with partners and suppliers in that space to help develop and improve supply chain that can produce standardized units that are more robust and custom fit to what we require for millimeter wave drilling, utilizing tens, if not hundreds of these units 5 to 10 years down the road.
Gotcha. I'm going to give you a call offline. We can talk about plasma arc technology.
Plasma is a great one. Yes.
Right.
Yeah.
So let me get to another question, and that led me to one of my questions. Is it Quaise's, are you trying to use the borehole as the pipe? Or is it the sleeve that's going to be the pipe? Or are you going to actually insert a pipe at some point once you have the hole drilled?
So once we have the hole drilled, we're, as of now, relying on installing casing or casing and cement to complete the wellbore completion for the purposes, not just keeping this hole open, but also being able to do the multi-stage type stimulation that we believe is needed for creating the reservoir. So there will be a need for long-term wellbore completion after the drilling process is complete. We are certainly exploring the potential for utilizing this vitrified liner as a long-term open hole, quasi-open hole style completion. But as of now, conservatively, we assume we require high temperature casings and cements to keep the hole open and stable.
Got it. Makes sense. Another question from the chat. Heat extraction. How do you ensure efficient heat extraction from super deep wells? What are the expected temperature ranges at these depths? I mean, your 450 is the 500 is the highest one I've seen. So,
right. We think temperature target, formation target temperatures probably on the order of 400 to 450 degrees Celsius. The reason for that being is I think we would like to produce that fluid at the surface right around the critical point of water, which is 374 degrees C. And then we're still exploring a few approaches and how best we convert that hot fluid electricity, in other words, the power cycle to be used, whether it's a traditional flash steam ranking cycle or a more novel binary water-water cycle, which we've published some research on at GRC and Stanford Geothermal Workshop this past year. In terms of efficient heat extraction from the subsurface, that we think involves definitely some mode of multi-stage stimulation. So isolating zones whereby you can create hydraulic fractures and potentially take advantage of those natural fractures that are likely already present in the rock for connecting these wells across a large volume of rock and with high surface areas within the fracture itself. And importantly, we want to make sure that fracture network is fairly uniform with its hydraulic characteristics such that fluid is flowing through all of those fractures relatively evenly and not just concentrating in one major fracture and fault that takes all the flow and thus solely extracts heat from that zone.
Okay, it leads me to another question that I've had, and it probably is going to lead on to the next question here. But when you drop cool fluid into that type of temperature, 400 to 500 C, what are you expecting to happen? I mean, I'm expecting a small explosion,
Right.
a fracture in the rock, and I mean, this is where you're going to create your reservoir, right?
We think we're very interested in exploring how temperature can play a role in the fracturing process. So I think you're exactly right that when you bring cold water down to these very high temperatures, there's a pretty extreme temperature gradient that's going to induce thermal stresses. Now, that's going to be a challenge with things like wellbore completion, where we want to assure the wellbore is not failing and collapsing because of that thermal stress. But for the purposes of fracturing, this could be a benefit to us targeting these higher temperatures, is that we don't just have to rely on hydraulic pressure for fracturing the rock. We can use that temperature difference to do it. And so this is something that, to be honest, a lot of fracture models aren't even yet built today to really model and understand. But certainly in the coming years, we want to develop the modeling capabilities and test this in the field to understand how temperature can play a role with fracturing.
Very cool. Next question here from the chat. Again, energy conversion. What power generation technologies, supercritical steam turbines, are best suited for Quaise geothermal? I think you just mentioned a couple. I mean, certainly the organic Rankine cycle, but the binary you had just talked about a little bit, maybe.
Yeah, maybe I'll expand on that a little bit. So organic Rankine cycle has certainly been the preferred choice for anything below, I think, 200 degrees Celsius and maybe a bit above 200 degrees Celsius. And that's owing to the lower temperatures favoring an alternative working fluid to be flashed to run through the turbine generator. Something that a colleague of ours has found is that when you look at temperatures exceeding 300 degrees Celsius for a binary power cycle, water is an advantageous working fluid for running through that turbine. And so if there are concerns, especially with water consumption and the corrosivity of the geofluid potentially degrading the turbine, a binary water-water cycle where we produce the hot geofluid and run it through a heat exchanger where it's passing that heat to a separate cycle of water that then runs through the turbine can be a potentially advantageous approach. And what we found through that modeling is that there's very little to no difference in efficiency or performance with respect to a flash steam Rankine cycle.
Cool. Very nice. Very good. Let's see. This next one is about carbon footprint. What is the estimated carbon footprint of deploying this technology compared to other clean energy sources?
Yeah, that one is I'm not going to have right off the top of my head. And the challenge for that, I think, is that geothermal projects have varied widely with their carbon footprint. A few naturally occurring reservoirs owing to either having a magmatic heat source down below or potentially producing geofluids from carbonates exhibit some higher carbon emissions for the first couple years before they drop down. I would err to say that I don't have an exact number, but I expect our carbon footprint with our approach to SuperHot EGS to be towards the lower end of geothermal systems in operation today. But that is highly speculative because, again, I think where there's variability with the carbon footprint in geothermal projects, it's often owing to the fact that the specific formation you're in may have higher, may yield some carbon emissions in the first couple of years of the project. So it's certainly lower than burning fossil fuels. But for some settings, and this has been observed in some fields in Iceland, for example, they did show in the first couple years that there was some higher carbon emissions from a geothermal field compared to other clean energy sources today.
All right. I mean, so how much kW or megawatts do you need to run the gyrotron?
Yes.
To me, that is the footprint that we're talking about.
That'd be the other aspect to the carbon footprint. And so the numbers I would use is that to drill full-size geothermal hole at our desired rate of penetration, the whole system, including the gyrotron, the purge gas, the drilling rig, it's going to be on the order of 3 to 5 megawatts electric power. And if we're in a remote setting, which is most likely, we're using diesel generators to run that drilling rig. If, say, we use that for a year, 5 megawatts consumption to drill 3 wells, we think from that well triplet, we could be producing 30 to 50 megawatts of geothermal electric power. And so the sort of clean energy produced per dirty energy consumed gets paid off within the first couple months of operation, provided we hit that power output goal.
Well, I mean, once the drilling is in and the power plant is set, you've just created a perpetual motion machine. You're creating the electricity that you're going to be using once you get up and running and this thing
That's
is
right.
installed and you're going. So
That's right.
That needs to be put into the whole equation when people are looking at this stuff. Next question, seismic risks. I think we talked a little bit about that, but how does your drilling method mitigate risk associated with deep geothermal, such as induced seismicity? Yeah, I mean,
I would say where risk could be reduced is that by going deeper in locations that aren't favorable for geothermal, we're going to be in locations that are less prone to any sort of seismicity. One reason I think we've seen instances of induced seismicity in geothermal and EGS projects to date is that the areas where geothermal and EGS has tended to be favorable are also areas that are seismically active. And a reason for that, I think, is best put by Mark Zoback in his book in Geomechanics, where he says that faults that are mechanically alive are hydraulically alive. So in other words, locations where you have earthquakes today are also locations where you tend to have naturally occurring geothermal reservoirs, owing to the fact of that natural seismicity helping keep faults and fractures open. But by going deeper, we could be going to locations where that seismicity risk could be reduced. Other than that, I would say the drilling technology doesn't really change the equation on induced seismicity risk. And in all cases, we plan to deploy an induced seismicity mitigation plan and monitoring schemes such that we ensure no significant seismic events get induced by the reservoir creation or production from the reservoir.
Okay. And at this point, we're talking about 6 kilometers, right? Between 2 and 4 miles deep.
That would be initial projects. I'd say our first pilot development, we're targeting 5 to 6 kilometers. And following that, we would like to scale that to 10, 11 kilometers, where we think a lot of, say, the Western US gets opened up for SuperHot EGS. Further down the line is when we want to explore going much deeper than that and greatly expanding the scale at which you can do this approach to geothermal.
Okay, we have a question about waste management. I just lost it. Let me get it. Oh, shoot. Waste management. What happens to the vaporized rock? And are there any environmental concerns related to this byproduct? I saw those sparks.
Yeah. Yeah, we don't vent those to the atmosphere for certain. So unlike what you saw in the lab experiments where everything was sort of open in a confined test chamber, when we're drilling in the field, the rock ash is kept contained and is directed at the exhaust outlet to a separator that separates all of the solid particulate from the exhaust gas, which is then vented at a high enough elevation, vented out into the atmosphere. And so none of the solid ash gets out to the atmosphere. We plan to keep that separated, confined, and eventually disposed of at a requisite disposal site where we see fit.
It shows up as ash. It comes out as ash, or is it just tiny little pebble? I mean,
Yeah, it's a mix
curious.
of condensed ash that was rock that was vaporized, that's very fine. And then there's a slightly larger scale of particulate that's more on the order of tens to hundreds of microns. That's basically melt droplets that are ablated from the melt surface from drilling.
At some point, you may want to test that, see if you're actually mining for gold or something.
Wouldn't be bad if we were.
No, it wouldn't be bad at all. Next question, regulatory barriers. That is a good question. What regulatory challenges does Quaise face in gaining approvals for deep drilling operations?
Yes, so I think there's certainly a host of regulatory challenges that applies to a lot of geothermal as well as EGS in terms of these have probably been repeated by many other entities, but geothermal projects today take longer to permit than oil and gas projects. And it's owing to, I think, some inefficiencies in terms of how these projects get permitted on federal land operated by the BLM, activities that require much more extensive permitting than are probably warranted. Like, for example, doing initial exploration work that involves little to no disturbance of the surface or subsurface. And so I think there's been momentum on the Capitol Hill with various bills intending to improve that regulatory process. I would say for Quaise and millimeter wave drilling more specifically, probably we're still working on identifying where there can potentially be regulatory barriers, but certainly one that's come up with just our lab testing are FCC regulations on the frequency that we're operating at with respect to not just our drilling technology, but also the diagnostics that we send down our borehole with the microwave beam, like the radar diagnostic that tells us our approximate depth of the borehole. And so we have gotten some initial permits for some of our lab and field trials to ensure we are within FCC guidelines, but that's an example of a more novel regulatory challenge to Quaise with respect to our drilling technology. And certainly speculatively in the future, if we find success with completing these wellbores with our drilling technology, in other words, with this vitrified liner I mentioned, then I'm certain there will be a host of regulatory challenges in gaining the right approvals such to utilize that vitrified liner as a deeper component of the entire wellbore completion.
I have a question. A 20 megawatt system that was developed by Quaise, how would you think that would compare to a 20 megawatt SMR, small modular reactor?
Yeah, I mean, it's a good question. I think for us, we want to similarly match the scalability that SMRs could have today, whereby we aren't just doing geothermal in the locations where geothermal is already favorable. SMR has no limitation. I would say similarly between both approaches, we can be fairly modular in terms of SMRs. They can modulate their power output based on how many SMR units they want to put for an installation. Similarly for us, we can be modular in terms of how many wells we drill for potential project to meet the demand specifications of the off-taker. So I think there's some similarities there. Certainly, there's a lot of SMRs that are technologically mature today, and we aren't there yet with our approach to geothermal, but we would like to be there. I think a bigger challenge maybe for SMRs, and this is not coming from a nuclear expert myself, though, is the geopolitical and sort of regulatory constraints for SMRs being nuclear fission technology. That's certainly, I think, a concern and a challenge for seeing how SMRs could scale globally as an energy transition solution. But certainly within the US, I think they seem quite compelling for what they provide.
Well, I do too, but I raised the comparison because, with the advent of high tech, wanting to build all these AI server facilities, They're talking about dropping an SMR right there. But I like your business model where you want to employ uh, uh, your gyrotron system right next to an existing fossil fuel power plant. And I think that's a very novel idea, and I certainly would encourage you to look at that here in Hawaii.
We'd love to. I
Yeah.
think Hawaii, not just for, needs and wishes for clean energy, but also for the availability of land. There's a need for power dense clean energy solutions. And I think that's another benefit to what we provide going deep and super hot is a more dense approach to geothermal scalability.
I agree. Let me jump back into this list here. Energy transition role. How does Quaise geothermal technology compare with, we just talked about this. I'm just going to ask it again now. Compare with nuclear and other power solutions for baseload energy needs. Okay. Fairly similar in my opinion. They're both firm power.
Yeah, that's exactly right. We want to help make geothermal a scalable solution to clean firm power, which I think is increasingly seen by many as a requirement for the energy transition to complement more intermittent wind and solar resources.
If these questions all came from Noel, man, great questions, Peter. I mean, you guys put some good stuff here. Financing and partnerships. What level of private and public investments is needed to deploy this technology at scale? It's a great question.
Yeah, I think the number that we like to throw out there for getting from where we are today to, say, building gigawatt scale geothermal well fields and power plants is $1 billion. And I think that's certainly a large sum of that is needed for the technology development, but also to begin to finance the first 3 to 5 geothermal project developments at super hot temperatures. I think in later phases, once you've validated and de-risked the technology and the reservoir, you can gain access to lower risk capital like debt from banks that help finance these projects further. But I think conservatively, I'd assume something on the order of $1 billion is what's needed to take us from now to, say, gigawatt deployments of super hot geothermal in the next 5-10 years.
Okay. Timeline for commercialization. When do you expect to have your first operational plant, and what are the main hurdles to commercialization? I heard you say 26 to 28. Is that right?
That's right. And I would say those dates are actually going to be more so where we think we can execute our first successful well field. I think as we learn more, we're seeing, it's definitely a challenge to get interconnected electric power generation in that timeline. So I would say conservatively by 2030, we would like to have a geothermal power plant putting electrons on the grid. But we are planning by 2026 to have our first super hot EGS reservoir completed and producing fluid at the surface, not necessarily producing useful energy, electricity, but de-risking that reservoir creation aspect while we are still de-risking the drilling technology in parallel. By 2028, we'd like to expand the depth and temperature from which we produce from that reservoir with the millimeter wave drilling, assume it has progressed on schedule. And then by 2030, we fully have the power plant built for producing electricity. And we are planning to develop some projects in parallel such that we aren't just limited to that one project by 2030. By 2031, 2032, we can ramp additional projects online because we've also been executing the earlier development phases preceding that.
Is that the project you're doing in West Texas?
No, the project in Texas, which is actually Marble Falls, Texas, is purely a field trial of the drilling technology.
Okay.
So we're going to a shallow granite body, drilling initially target depth of 100-meter holes, and next year extending that to 1-kilometer depth, not for the purposes of geothermal production, just for the purposes of validating the drilling.
Sure, it makes sense. I think we've run out of questions in the chat. Let's see. Let me just check Q&A. Oh, we got some Q&A stuff. Okay, here we go. How does temperature relate to BTU produced? How much purged materials need to be disposed of? How much power is used to use the megawatt MMW drilling procedure? Okay, we talked about that, to drill to 10 kilometers.
Right. I think just to put some numbers from what we've modeled, if we are flowing, I believe, 60 kilograms per second into a reservoir at a temperature of around 400 to 425 degrees Celsius, we believe that's going to get us a 30 megawatt electric number from either a well doublet or well triplet. In terms of that question of BTUs per well, purge materials, I have to do some. I'm trying to remember the back of the envelope calculation for this, but if we're drilling a 10-kilometer hole that say is a depth a diameter of 8 inches, I believe it is about 300 cubic meters of rock cuttings that we're having to remove, store, dispose of offsite. So I might be off by an order of magnitude, but I'm pretty sure it's 300 cubic meters. And then is there one additional question there?
Let's see. Well, there's more questions. Let me go to this next one. Geobalancing concern from seismicity. Survey of North America geosites with possibility of EGS implementation in the next 10 to 20 years. I'm not sure what the question is there.
Yeah, I suppose what I'll just note there is seismicity risk from naturally occurring seismicity is something we definitely take into account when evaluating potential project sites.
Operation and maintenance concern challenges. I mean, this is stuff you're going to learn about.
Right. Certainly for the drilling, we're learning by doing in terms of what's needed to ensure these systems are maintained, to operate for tens, hundreds, thousands of hours. With respect to the reservoir and power plant, I think a very important operational concern to note is precipitation. Especially at these high temperatures, we can expect there's a lot of rock that's probably going to be dissolving from chemical reactions, and that solution has to precipitate somewhere. And so managing, precipitation from the geofluid is something that's already done today for a wide variety of naturally occurring geothermal reservoirs and power plants, but it's something that we will have to take into account as well in terms of how we operate our reservoir, what sort of equipment we have at the surface for safely separating and storing that solid precipitate and not sending it into the turbine, of course, where it can damage materials.
Okay. This next question is in relationship to what we talked about before. With recent hype of artificial intelligence, increased demand for power guzzler data centers, and data mining needs for block technology, et cetera, I'm assuming that is, how would you fit in? And we talked about that. You could fit in just the same way an SMR would fit in. You would drill your hole right next to the facility.
That's right. Yep. And that's really, I think, the value in our approach to geothermal is that we can co-locate the power source with the load or the demand. And I think I speculate there's going to be increasing interest from these hyperscalers to do that as they find their ability to deploy these gigawatt scale data centers is limited by the ability to get that power from the grid and waiting for it via the interconnection queue.
That's right. Next question, reliability, safety, environmental impact from a byproduct generation, neutralizing the environmental impact. I think we talked about that. I'm assuming that he's talking about the byproduct of the molten rock and stuff that comes out. I'm assuming you're talking about testing it for hazardous waste type things, but
right.
Yeah.
Yeah, I'll just note we're not necessarily too concerned we're producing hazard products from the rock or the drilling process in terms of the chemistry. It's more the particle size. Then this is why we want to make sure that we are not venting these particles out to the atmosphere because they're very fine, qualify as like PM 2.5, which is pretty, definitely something you don't want to be breathing in. And so we definitely ensure with our exhaust collection system to store, collect, and dispose of all of this rock cutting material that is very fine, such that it doesn't end up in people's lungs.
And anybody that's standing around it's going to have eye goggles on, right?
Yes.
That, I believe. Oh, we got one more. What about the use of abandoned oil wells? Good question, Mitch.
Yeah, I've always been curious in this application because I've seen it come up a lot in conferences. And I know there's various companies looking to do this and potentially in Texas. I think I will note a constraint for us and why we don't believe it will work for our approach, and then maybe my own concern about the larger picture. So for our drilling process, we do require this upper section of the hole to be drilled relatively straight for the waveguide to be inserted, because if that waveguide is bending not to our design, like we'd want to do with directional drilling, we have the potential for increased attenuation and energy losses in the waveguide. And a lot of these older oil and gas wells were not drilled with that constraint, so they often have this tortuous corkscrew type geometry that wouldn't necessarily be compatible with our drilling approach. A secondary concern for us, as well as I think other potential developers using to repurpose these old oil and gas wells, is that these wells were not necessarily designed and completed in mind of producing very hot fluids. And so I think I'm sure there are wells out there in the US that maybe are able to meet this requirement, but if these wells are going to be extended or plan to be producing very high volumes of hot geofluid, they need to have been designed with that specification originally, or if not, there's going to be a very costly sort of workover intervention needed to repurpose the well such that it can accommodate a fluid that is not only higher temperature, but produced in much higher flow rates than what they were initially intended to produce from with respect to an oil and gas type project. So I'll admit it's not my area of expertise, certainly, but I do think there are some concerns for this repurposing of oil and gas wells, that not all of those wells may prove suitable for geothermal development.
Okay. I mean, it seems to me the first thing that strikes my mind as a hazard, an oil and gas well that's been capped, now uncapped, and you're going to put 3,000 C of arc plasma down there. Would you expect any sort of flame up? If there's any fumes down there, I certainly would.
Yeah, I would prefer to avoid it.
Yeah,
That's for sure.
yeah, I wouldn't want to be putting a hot poker down that hole. Anyway, that's the end of our questions. Lost my screen.
I'll jump in. So I think we're about at the end of that, at the end of this. And Matt, I want to thank you very much. It was a fascinating presentation. And I think, certainly conceptually, the track that you're going down, I think is very much worth pursuing. If we have I think we're at a point now where it's really clear that if we want to transition away from fossil fuel for all of our energy needs, solar and wind are not going to be able to do it on their own, along with battery backup storage. We have to have baseload power, and there's only two ways to get it, and that's geothermal and nuclear. I mean, one or the other, and I don't think either one can be that silver bullet. So the opportunity to be able to be site specific with a reasonable expectation of output capacity would be a dream. So I for one hope. I mean, I hope you're very, very successful, and sooner rather than later, with the technology you're developing. So again, I want to thank you very much for joining us today. Is there anything you wanted to say in closing, Russ?
I just wanted to say thank you, Matt, very much. Extremely interesting and exciting for me to see the technology and where we're headed. You know, you had a year in your slide, 2050. The state of Hawaii has a goal of being 100% renewable by 2045. Without this type of technology, there's no way, no Ice Cube's chance, and you know where, of achieving that without them adopting geothermal as a priority technology, because they're not going to do it with nuclear. Nuclear
100% agree, Russ. I mean,
still going to take how many years for them to fight that one out?
We're a month into the state energy office having made the case for building an LNG import terminal. So I think the powers that be understand are realizing the limitations of intermittent clean power.
Yep. Anyway, thank you again.
Thank you, everyone, for the opportunity.
All right. Thanks, everyone, for joining us. I hope you all got something out of it. I know I did. Aloha, and thank you, Sustainability Energy and AEE, for co-sponsoring this wonderful webinar. Take care, everyone. Aloha.
Aloha.